Okay. So let's kind of recap where we got to. We've looked at so we'll see, depending on how far we get. If you, how many have had me before or something? Okay. So you know I give a review sheet before the exam, so you'll have a chance to look at that, and you get that at least a week before. So I will go through and see if we've got what we've got covered, and I'll get the review sheet put together, and I change a few lines in it depending on how far we get. Try to fit the exams, space them fairly evenly. We'll have also not a dedicated review day, but a day allocated to as much review as you would like to generate by asking questions. So I will not try to recover all of the material that I've talked about since the beginning of the semester, but I will respond to whatever questions you have based on your review. You're looking at the review sheet and being able to go through that. So I will, I'll finalize that in an announcement. So I'll put it on Canvas. And so it'll cover pretty much through chapter 1 right now, but I'll detail it for certain, but give me an idea. We've been looking at something called regular languages. And we've learned some stuff about what you can do if you have two regular languages, the operations that you can do on them and still have a regular language. We call that what do we say if you have one regular language over here, another regular language over here, and you can do this operation on them and still end up with a regular language? What do we call that condition? Or what is, yeah, closure is a kind of, should have been a dentist. Pull on teeth. Yes, so we can say that that operation, or that the regular languages are closed under that operation. You can apply that operation and you still get a regular language. They're closed under the union and intersection. Put those together. Also under concatenation. And we can show these and star. So the star operator is, we talked about, you can take any number of strings out of that language and add them together, any combination of any of the strings. And you still get a regular language. And the proof of that, we're not going to do a detailed verbal proof, but we'll do proof by construction to kind of affirm this. Now that we have non-deterministic automata and that handy little epsilon move, right? So we know at this point, the DFA, there's an equivalence, right? Any language that can be accepted by a DFA is regular, and every regular language can be accepted by a DFA. We point that out just because when you think about, what regular languages are pretty regular. The fact that you can loop and you can go between different states and repeat the states, those kind of actions define what we mean by regular language. And what else we've added on there is an NFA is equivalent to a DFA, and because is it true that a DFA is a special case of an NFA? Yeah, sure. We said that the NFA is a little bit looser, but a DFA is a specific instance that meets all the criteria of a narrowed part of the criteria of an NFA. So if it's a DFA, it also meets the conditions of a DFA. If it's a DFA, it also meets the conditions of an NFA, but not the other way, right? An NFA allows epsilon moves. We went over in some detail the differences between those. So you should be able to discern what those differences are and enumerate or pick them out of a list or even write them down. Just to mention, my review sheet tries to capture this is what you should know and this is what you should be able to do with it. I tried to give you an idea of, right, there's very different ways of quote learning something. I didn't use air quotes, I just used verbal quotes there. I could air quote it if you wanted, but I think it's sufficient. Learning stuff involves different levels of understanding, different levels of mental operation. One of the things that I try to avoid is rote memorization as being one of the lowest levels of learning, right? And the most elusive types of learning as well, because rote memorization requires continual repetition. That's the stuff that is going to evaporate after the exam and not what you'll likely be able to carry away as far as something you gained out of the course. But there's going to be a few definitions, stuff like that. I will list that kind of stuff on the review sheet to say, if you need to know the definition of this, you need to know what this is, you need to be able to define a DFA either as a picture or in the formal listing of the 5 elements of it, that kind of thing. So those will all be listed, and you'll know kind of to what level do I have to apply myself to be able to do stuff with this for the exam. Okay. So we want to look at a quick proof using the NFAs. We proved, or the fact that there exists a conversion from an NFA to a DFA is proof that they are equivalent. And he goes into some detail that I'm certain you will be perfectly satisfied with the fact that you can convert this to this without necessarily proving that they are identical in extreme theoretical detail. So we'll use the NFA to prove a couple of things. in particular, to prove the union, how could I do that by construction? Well, if I can, here's the underlying idea, right? If I can build an NFA for each one of these operations, then that is kind of self-evident proof that the result is also a regular language, right? Give me an NFA or a DFA for one language, give me an NFA or DFA for the other language, and if I can apply that operation to those through construction, making an NFA that does that, then it must be regular, right? The resulting NFA is also a regular language, which is the whole point of our closure, right? If you do this, any one of these to a regular language, you still get a regular language. So what would we do for union? Union is what? It says take anything from either one of the languages and we can do something like this. This is kind of the pattern. We'll have a start. Now union says pick anything out of this language or this language. So what we'll do is an epsilon split, and I'm just going to kind of draw okay, so I have a start state. This is my resulting NFA for union. And this follows essentially what the book shows you as well. The essence of it. So I have an epsilon move that gets me to the start of this DFA, and this one takes me, there's only one start state, right, in any DFA. So this epsilon, I start in start state, you go, okay, on an epsilon move, I can either go to the first DFA of language 1, and this one is the DFA for language 2. Then I can go all through that, and then from any of its, I'll just have epsilon moves from its final states get me to my final state. And similarly, what do we think? Would this represent the union of these two languages? Union, remember, you should be able to, express what the union of two languages means. It means you can pick one from either. So you're basically making one NFA out of the two DFAs for the language. They could be NFAs as well. Kind of being in the simplest terms. And this just says, basically, if you want the union of those two, instead of taking either this language, taking this language, or you could take this language, is the idea of the result of taking one from either one is you can epsilon move to this one, go through all of it, and then jump to the final state over here. So the combined DFAs, or you could go down this path, go through all this one, and if you can get to the final state, an accepting state on this guy, the epsilon move to this guy, and what we would do is okay. So when we get all done with it, we only have one final state here. So everything that was a final state over here, we don't want to stop, or we don't want to accept when we get there. We want to force it to come out over here. So does that seem plausible? Does that seem like a reasonable? Clearly, we have a new NFA, so it must be, the result must be of a regular language. And can we convince ourselves that it does the union? Well, we can pick something from either one of those two languages, and we're just basically picking a path. Will get me through one or through the other. And of course, if the string is not in the language, then it'll stop somewhere in here and will not be able to get up to the final state. So that's the gist of I do recommend that you read through the book. It helps if you have a little lead-in explanation in front. I like using, I add this onto the end because of the book that I learned out of. Kind of modularizes the whole thing and does the construction in a consistent way so that they always end up the same. You know, if you were building something and you end up on page 59, 59, he's doing basically an NFA to recognize either one. Basically, a new start state, and you epsilon into one or the other of the DFAs. So it would be sufficient, right? Technically, you could leave this guy off, but I like the idea of kind of saying, you know, this is kind of self-contained. I guess it's like modular programming. This one is self-contained, this is self-contained, and then we just make this nice little connection between. Okay, but that you should be able to see pretty evidently that is equivalent, completely equivalent to page 59, where he does the construction of the NFA for union. Similarly, page 61, he does the construction of the concatenation. Concatenation L1 concatenated with L2 says pick any string that is in L1 and immediately follow it by a string from L2. Okay, so what would that look like? I'm using the same kind of idea. And again, his is barely simpler. He leaves off the kind of external start and stop states. But I would so concatenation again. How are we proving? What is the proof by construction? Consists of, we take two NFAs or DFAs, we combine them together in an NFA, and the result must be a regular language by definition. So we would, let me be consistent here. What crazy is that? Dashed line around this guy. This is going to his Q0, his start state. So you can epsilon into there, and then from whatever final states, we don't want them to really be final states anymore. But what we want to do is epsilon from each of the final states here, that each of the states that were in the original final states, we'll go into the start state of this guy, and I like the idea of, again, making it modular to do to a final state out here. And so this should make some logical sense. The idea of concatenation, take a string out of one language, write it down, and then put a string from the second language right next to it. So this would give you the string, some string, anything you wanted out of the first language. We would epsilon then to the start state of the second language, DFA, and if you combine them like that, you end up with an NFA, so that must be regular as well. Following, what's the idea of using the machines, using the building off of, okay, we've done all this work with the NFA and the DFA, and we've got some ways to define regular languages. So now, we might ask that question, what happens if you do the union, or the concatenation, or the star? And the answer is, you get a regular language. And so this is kind of the justification for those. The last one is the star. Star always says 0 or more iterations. Somebody brought up, when we get to regular expressions here shortly, there's you'll see the use of the plus. Star is 0 or more, any number, and the plus sign is just an indication of 1 or more. So it removes the empty string, it moves the choice of having no selection. This is the same as, so something like A plus is the same as saying A star. And you have to have at least one of them, and then as many as you want calling that. Oops, I should be concatenation, not concation. So star says so if I had a language L1 equals no, just that's easy enough. So a couple of strings are in this language. It's a finite language. The star operator gives me an up to infinite number of repetitions of that. So L1 star would include the empty string, I should have put. So I could pick 0 elements. I could pick dog, cat, I won't enumerate all of them. I should say not. Right, so again, see if you can come up with, real quick, think through this with me. Can you come up with a way to put a how could you connect this? So it would be the star operator. So my drawing is a little different from his. Again, I'm emphasizing the kind of modular nature that you can just take a little, this is the equivalent of a drawing of the DFA, and apply these steps to them to get a result. And you can do it the same way every single time, less caring about the number of steps. What do you think? What would you do? Yeah.
So I suppose you could put Q0 into your little DFA there on an epsilon.
Okay, we get epsilon here.
And then epsilon also takes its accept states to the actual accept state.
Right?
And then you also just, on epsilon, go from the accept state back to Q0.
So to this point, we've just got exactly the same thing as the DFA. We haven't added any more. But we can take an epsilon trip back. And again, you might rightly treat this as a little obsessive, compulsive, I don't know. But you hopefully are seeing a pattern. I'm doing it purposely with this kind of putting the epsilons around. We're missing one option that the star gives you. Let's see what that is.
Since it's 0 or more, it might just be able to just go to QI.
Yeah, is that your answer?
Yeah. Is it epsilon?
Yeah. So the star lets you take 0, and so technically, if we left this off, it would be plus. But we're trying to prove the closure of the star. So if you didn't have that, if the empty string was already in, so the empty string is not in this language, but it is in the star of that language. But it could be in both. If the star, an empty string or an empty set is inside of here, I should say empty set, then it will appear in both. So what I'm saying is from here, there may have been an epsilon that could have gotten you to an accept state here, and then epsilon gets you there as well. So, but like I said, I'm trying to think of it. The best way I wrap my mind around it is just make it all modular, and you do the same thing every time. So you epsilon you make your own new Q0, the epsilon of the DFA's Q0, the epsilon out of its final states to your new final state. And then you just put a big loop around the whole thing. So you can go as many times as you want back to here and go through the whole thing, or you can start here and just jump to the end. So everything that builds the definition of the star operator. And again, this is an NFA, so it must be regular. Okay. So again, I'm not doing anything. I'm doing something a little more explicitly than what the author does. So I'm drawing it out a little more clearly what's happening, just to emphasize the definition. But you get pretty much the same what he shows here, and I just don't like it as much. The authors back in the old days when the pterodactyls were flying overhead, Um, the textbook was Aho and Ullman, famous computer science authors of the 80s or so. But they built it along this nice kind of modular way. So you get the equivalent. You can look on page 62. He has his version of it. Yeah, question, comment.
So I understand how we're able to combine the DFAs through union, but what's the difference between that and intersection? Because I'm trying to figure out that last little step to get to the accepting state, but I can't get it.
Ah. So in the intersection, you have to go through both. I think I'll have to circle back on that one. We know we can build, well, I mean, I'm trying to think if there's a way to build it in one step like the union, and it's not seeming obvious to me. But we know how to build a DFA from our NFA and then flip the accept states for the union. So by that, we can build it on that basis. That's the obvious one. Right, because we don't really have a machine, we don't have an easy construct. The point is we can't prove intersection using a simple construction like this. So what we would have to do, we can prove it by complementation. Right, we know that in addition to these major stated ones, they're also closed under complementation. That if you've got a DFA that accepts a language, you flip the accept states, you got the complement of that language. So from the union one that we started with, we just turn that into a DFA, which is going to expand the states, and then flip the accept and reject states, and you've got the intersection. But I will think about that further if there's a direct construction. I can't think of one off the top of my head. This leads us to regular expressions. How many have had, let's see, along about, should have been exposed to regular expressions like in Unix class, depending on how much time they had. You could have seen those, that regular expressions are used in some of the matching or search criteria for in Linux. You can also, has anybody ever used them in Java? Seen them use them? One of the things interesting in that at my last industry gig, I had someone who's greatly enamored of regular expressions in trying to recognize. And it is it is an alluring trap. What we're trying to do is recognize strings, certain what we're trying to recognize is length-bounded input strings. I was actually reading data from a file where, like, the first 8 characters are an ASCII label, the next 10 characters are a real number in a certain format using ASCII characters, and so on like that. And this one person started building their recognizer of that stuff. Right? It's kind of a let's see, using a sledgehammer to drive a tiny brad nail, small nail, because all we had to do, right? So these fields are fixed length. It's just an input string. We're reading one line at a time out of an input stream, and it's like the first 8 characters are always this. The next 10 characters are always this. And so what would you do to pull it apart, parse it? Well, you copy the first 8 characters over to part 1, copy the next 10 characters over to part 2, right? Pretty straightforward operation. It's not uncommon at all in dealing with messages into systems across communication line. But they kind of built this regular expression, and using XML format, you can specify lengths and stuff. And what the problem, and I was because I dealt with it, I was at least skeptical, because I was going, the easy thing to do here is just pull the freaking characters off of the, get them out of there, instead of trying to find patterns of the string. And so, sure enough, what happened is it was matching a lot of the time, but every once in a while I'd get this anomaly because they hadn't thought of the character. There are certain limiting, like this can be alphanumeric, and it turned out there were it was alphanumeric or possibly a dash, right? Which wouldn't have bothered you if you just took the characters. You never would have worried about that. But the little dash in there wasn't anticipated, and so all of a sudden these errors start popping up, and then it throws off the whole distancing and what it recognizes, and error, try to catch things. It just turned into a lot more. What looked like this really cool, elegant solution on the surface turned out to be a way more messy solution, because you couldn't, kind of like with our DFAs, where you might be easy to exclude all the stuff that you should exclude, but you exclude too much, or you accept everything you should, but you accept too much. That was the kind of problem that was coming up through using the regular expression. And also, they are not particularly fast in the Java implementation that we were using. They're actually, when you're doing, thousands of things, it's always, the problem for all of us is when you try your algorithm on a few good cases, right? You can't try everything, so you try a few good cases, think your testing is complete, and then you try it on a large number of cases, and all of a sudden you find out, oh, wow, something's really slowing this down when we try to do 100,000 lines. And certainly the Java handling of the regular expressions was costly, because it was doing a whole bunch, again, take the characters, just pull the characters off, versus doing all this pattern matching stuff under the hood that you don't even know is going on unless you understand what the regular expression is doing in reality. And it's kind of like, well, probably the equivalent of running it through DFA-like processing to check all the combinations and stuff. Got ugly. All right, but regular expressions, let's define what they are. Let's see if my where's my board gonna end on me? There. So we're looking at the definition on page 64, what a regular expression is. As you might guess, what we're going to add on to our list over here is that regular expressions express exactly defines a regular language. They're equivalent. So if you can build it, if you can define it with a regular expression, and it is a regular language, and it cannot. You could also build a DFA from it. You could also port it. You could also build an NFA. So use regex, common term. So a single character out of an alphabet is a regular expression by itself. What we're going to do here is, this is kind of a recursive definition that we're going to build on. Start with, well, empty string is a regular expression. The empty distinguishing between an empty string, which is a string of length 0, and the empty set, which is nothing. So this, the union of two regular expressions, where each of those are regular expressions. So you can union them. This might look kind of familiar. Taking a regular expression followed by a regular expression is a, you guessed it, regular expression. And then so what we just did is maybe you see the logical track here now. We started with regular languages. We said they are equivalent to, can be expressed by NFAs and DFAs, automata. We can show that the regular languages are closed using those automata and having a methodical way of building the union, concatenation, star with a machine, which we said already, if it's a machine like that, then it's regular expression. And now we just said these union, concatenation, star are all applicable to any of these regular expressions. So this is recursive, right? It's defining regular expressions in terms of regular expression. And so you can do any combination of those things as many times as you want and still get a regular expression. So what do regular expressions look like practically? The one little thing that they this author adds is the plus and the star, like what I showed over there. So you don't need it. It's a little bit more of a shorthand. Like a plus operation is exactly the same as this. So you don't need it to express regular expression. So we have another. I want to look at some examples and use a few. We're going to come to the theorem that says this. And the proof will be a rather complex construction that will not go over in detail. It takes a couple of pages to show the equivalent and comes up with the idea of a generalized non-deterministic finite automaton. If you look on page 71, it kind of summarizes. There's a long process to get to go through the construction of a GNFA, generalized one. We're not doing any of that, so we are omitting. A cheer went up from the crowd. We are omitting page like 67 to 76. But we'll do. We'll show some equivalences between. We won't go into the extreme detail of that construction. And then, yeah, probably next time we'll start talking about the one type of proof that we will focus on in this class. So we'll do all of that next time. So let me finish off with looking at some regular expressions and making sure that you understand what they mean. So let me make sure that I understand. Remember that stuff I was talking about, the rote memorization? Sometimes you can't get rid of it. So I have to okay, he's going to use the union operator. Maybe I'll show both to be complete in case I slip up. Okay, so what would something like this what does this mean? What what a string, this is a regular expression. Parentheses just group elements for applying the operator on the outside for putting that star on. So it means the BB, the two elements together are repeatable, 0 or more times. So this would be what, a string starting with A, ending with A, and having any number of pairs of B's inside. So something like, is this in there? No. I've got the red marker and I'm not afraid to use it. However, something like that is in there. But you have to watch me, right? Make sure you have to have pairs of B's. So that's in there, but this is not. That guy. Right. So the repeatable thing is 2 B's. And as soon as you vary from that, if you put a second A in there, you're already off. So can you build a DFA to recognize that language? Sure. What would it look like? Oh, you confident DFA experts. That's good. That's good. The only thing we have to fear is fear itself. Let's do NFA because that's actually a little bit easier. What do I want?
Go to Q1 on A.
Okay.
Q1 goes to Q2 on B.
Oops. I jumped ahead.
Oh, that's not what I was going to suggest.
Oh, okay. We can actually. Well, there's more than one instruction. Would you like to do this?
That's what I was imagining.
That'll save us a state.
And then Q1 goes to Q3 on A.
Q2 goes to.
No, Q1.
Oh,
Oh,
yes.
oh yeah.
Alright. So, do we agree?
There have to be a pair.
No, you can just go AA and that's fine.
Yeah, it's 0 or more. We could have just AAs in there.
If we go A from 2 to 2, there might be series of fails there, I think. This is the DFA.
Yeah, if you put 8 in there, it should fail because that's outside the.
Yeah, this will, as an NFA, this is, that's going to be a dead end, right?
Oh.
Try to put another A in
I
there.
thought you said DFA.
I then cheated and said it'll be easier to do an NFA. But we could turn this, we could just fill in the gaps here if we wanted to. You have to have an A, so if you see a B here, what this is going to go to our friend, the dead state or null state, right? See an A, this guy doesn't have a, this has an A, this has a B, so he's done. This guy on an A goes to U.
Then Q3 null underneath that.
Yeah, in Q3, let's see, yeah. Once you're there, you're there. So that makes it a DFA. It's probably a good construction process to build a quick NFA that gets you what you want, and then fill in the, everything else is going to be not that, right? Let's do, if we can do another one. Got all these are out of the book. So. Oops, that's my guideline. So, how about, here's one. Tricky. Okay, so there's the regular expression. It's actually pretty hard to put this one into words. You have to start with a 0 or a 1, and then end with a 1-1. So the union is either or. I can pick one or the other. Other ways of writing that might be, you see something like this, an alternation bar, which means or, same thing. Or sometimes people use the plus. Those are all regular expressions. These are probably more common than using the union that our book does. But you should be able to recognize those. Just in general, you're going to see any one of those possible in regular expression. So point is that these are dead marker.
Oh no.
You have protective gear on? You're in the path, you're in the glide path, perhaps. You're trying it. I'm not getting the height, The table's kind of bothering me here. The table's kind of... And so you get an assist. Okay. So this is 0, starts with a 0 or 1, ends with a 1-1.
So in the regular expression, would the use of that union imply 0 or 1, or could it be 0 and 1?
No, you have to pick one
It would be
out of there. Yeah, it's saying the union of, it's an either or. Good question, though. So it starts with a 0 or 1, ends with a 1-1, and then in between, you can have nothing, or you can have whatever's inside here as many times as you want, and they can vary. And so the common denominator is going to be, it's going to have a 0, 1 at the end of that little guy, and 0 or more ones
I
at
thought
the
that
front.
was concatenation.
Well, it is. It's a concatenation. Oh, that circle is a 0.
Okay.
That is a 0. And so some patterns that fit that might be 1, 1, 1, 0, 1. It's always going to end in 0, 1, right? And then just 0, 1 with no ones, but you can repeat any number of times that same pattern. So that could be, these could be chained together, right? So all of this could come between your 0 or 1 and your 1, 1.
Makes no sense together right now.
What's that? You did? Did or?
What specifies a required value? Since it's optional to have like.
If it doesn't have a star on it, then
Oh,
you gotta have it.
gotcha.
And you could have, parentheses usually are used to group stuff that's gonna be repeated. Or things that are ORed together with the union. So you have to have one or the other of these.
Yeah. Okay.
And so, you could, as an exercise, you can see if you can come up with the DFA
DFA.
for that, or an NFA. Should we do one? We can do it. We can do it.
Yes, we can.
All right, a 0 or 1 is required, so we have to have at least one character there. And then optionally, we can take a trip around to do this thing or not. And then we need a 1. That'll get us to our end state. So this is good so far. If it's an NFA, I got both shoes untied. Make for make for a great fall, and I don't mean autumn. Okay, so optionally, you can take a ride on the one. Oops, no. You can take a ride down to the 1 star, if you like, as long as you take back a 0, 1. What do you think? That work?
You good in that big, bro?
Seems like that's.
So we're forced to take a 0 or 1, and we're forced to end with a 1, 1. That looks good. And then optionally, you can have 1 or more of the 1 star 0, 1 sequence, right? You can take a ride on that as many times as you want. So in spite of the entertainment value, I will go ahead and tie my shoe. The potential entertainment value. And it would be recorded, so. So I do it over here. All right, I think we'll stop there, and please attempt. We are skipping up to page, so basically 67 to, I say 76? 67 to 76 is skipped. And then the pumping lemma. The pumping lemma is usually a somewhat difficult concept. It can only help you to read it through page 77. Maybe I'll throw an announcement out there for it to remind you. 77 to 82. Trying to read through that once is probably going to help. We'll spend a little bit of time on that next time. And we'll see you then. If I don't see you tomorrow, then have a good weekend.